Okay, my today's topic of discussion is galvanometer. Now, before entering into the subject about galvanometer, let us say something about basics of a galvanometer. A galvanometer is basically an electrical instrument which is used for detecting or measuring small amount of electric current by movement of magnetic needle or some coil that is suspended in between a magnetic field. Now, depending on the mode of operation, I mean the type of operation, type of damping we used, we can use this instrument for the measurement of small amount of electric current, or sometimes I can use it for the measurement of electrical charges. Now, these two case of determination depend on actually the mode of operation as how you are operating the instrument. Okay, now before start with galvanometer, let us say something about some basic theoretical aspect of this topic, that is Lorentz force. So what is Lorentz force? Lorentz force is basically a force which is of the type of magnetic force that act on a charged particle when it is moving through any magnetic field. Now, as I mentioned here, if a positive test charge, let us assume that small q is a positive test charge, is fired with a velocity v, which is obviously a vector, through a point P, and if that particle experienced a sidewise force F that acts on the moving charge, if there exists a magnetic induction B, then at that point where this magnetic vector B satisfies the following relation. That means if I fire a positive test charge with a velocity v in a magnetic field of field strength B, then the charged particle experience a force which is F is equal to Q into V cross B, and the F is called the Lorentz force. Now, as you see in this two figure, if the charge is positive, then this is the direction of firing the particle as if V. This is the direction of magnetic field. Both are in perpendicular to each other, and obviously as V cross B here, so the resultant magnetic field, which is Lorentz force, or force, that is Lorentz force, that acts along perpendicular to the plane containing obviously V and V. And if the charge is negative, then the force will along opposite direction. Now, with the help of this Lorentz force, I have to derive how a current carrying conductor behaves when it is suspended in a magnetic field. Okay, now assume that the conductor which is carrying the current is of course cylindrical in form, because when I come to the point of construction of galvanometer, you can see there that there is a cylindrical iron core present within the center of the ballistic galvanometer, and the coil on which the wire are wind up, that particular thing is of course cylindrical in cross section or rectangular cross section. Now consider dl length of the conductor which is under my investigation. So I am interested for this dl amount of length of the conductor which have a cross-sectional area A and it carries I amount of current. Then if it carries I amount of current, then the n number of charge present per unit volume, then the total charge resides within the cylinder of length dl and area of cross section A, obviously n into A into dl. Now each charge carrier of amount q charge, so the total amount of charges that contain within the cylindrical cross section n A dl into q. Now if the cylinder is kept under the influence of a magnetic field B, this is the total amount of charge, and this total amount of charge experienced Lorentz force. So the Lorentz force will be F is equal to Q into V cross B. Now here Q is basically N A dl into Q. Now in the later section I can see that N A dl into Q V cross B. Now N A as V and dl, that is the direction of the investigating length and the direction of movement of that particular electron, is parallel to each other. So I can just interchange V and dl and this equation remains as it is. So NAV into Q I into dl. Now if NAV into Q, this represents the total amount of charge crossing of this cylinder per unit time. So this is basically current. So I into dl cross B. So for a finite length conductor, the force exerted on it when it is suspended in a magnetic field is equal to F is equal to I integration of dl cross B. Now if this B is uniform, a constant, or I can say B is not variable at point to point of the conductor, then the integration will becomes more simpler and it will be F equal to I dl cross B. So this is the force experienced by a current carrying conductor when it is subjected to a magnetic field B, and of course when it is subjected to that particular magnetic field, it carries I amount of current. Okay. Now how can you measure the current, or how can you measure a charge through this same galvanometer? The mode of operation is when I am going to measure a current, then the instrument used as moving coil or suspended coil galvanometer. In this case, coil experienced a Lorentz force when small amount of electric current passes through it, and when small amount of electric current is passes through it, the galvanometer are kept in such a situation that it experienced a critical damping. So as it experiences a critical damping, then the indicator or the needle of that galvanometer becomes fixed at any point until I amount of current flows through the circuit. And in the second case, when I am going to measure a charge through a galvanometer galvanometer, I can use plainly different situation. The situation is that the ballistic galvanometer is used in such a way that when a charge passes through that particular galvanometer coil, it experiences a momentarily force. That means for a fraction of time it experiences a force, and when that particular fraction it experiences force, the particular needle or the indicator deflected, and that deflection become small if I impose a small amount of damping on that circuit. Okay, so in this case a small damping motion is present for the galvanometer. So I think you can familiar with these two types of use of galvanometer. Firstly, when I'm talking plainly, I'm talking about this current, measurement of this current. How can we measure a current of a suspended coil galvanometer? Then at the last part I came to the part of ballistic use. Okay, now I can show you some picture how the ballistic galvanometer is look like. So this is basically a ballistic galvanometer. Now if you go through the ballistic galvanometer, the construction is in this form. This is basically a horseshoe magnet. I came in detail discussion about the construction of this ballistic galvanometer in the later part, but this is a horseshoe magnet, and within the pole of this horseshoe magnet there exists a cross-sectional area on which a wire is wind up. Okay, and this frame is basically made up of shear aluminum, and there exists a fixed iron core within this cross-sectional area to make the magnetic field uniform throughout this coil. Now this whole thing is suspended from the roof of a fixed part, which is this roof, by a phosphor bronze wire. Phosphor bronze is basically very hardy wire, but it is very flexible also and too much costly. Now this is a mirror which is fixed over this phosphor bronze. Okay, and I kept this whole arrangement within a metal casing. Okay, so as you see here, at the outer part of this galvanometer there exists a transparent region through which only this mirror can be shown. So I can see the mirror through this glass plate, and I use a lamp and scale arrangement to measure the charge. Okay, now if some external light source is incident on this mirror, it reflects back, and it reflects back on a scale. Now depending on the movement of this image over the scale or the spotlight, I can measure my required variable. That may be current, that may be a charge. Okay, now this is another cross-sectional part of this galvanometer. Now this thing is connected to a wire, and the last part is connected through another wire, and this 2 points are connected through circuit diagram or external circuit. Now here a detailed construction is given, or the cross-sectional part of this instrument is given. This is in its horseshoe magnet. F is basically phosphor bronze wire, M is a mirror, and here exists a spring which gives the oscillatory nature of this phosphor rectangular cross section. Okay, now what is the principle of this action of this galvanometer? Say a rectangular coil is suspended in a magnetic field, and at the same time as it is connected through an external circuit, obviously some amount of current is flowing through this circuit or through this circuit. Some amount of current is flowing. When the current is flowing through the circuit, then this rectangular coil experienced a momentarily force, and the moment, due to this momentarily force, it is moving through this magnetic field. Okay, so current flowing conductor under magnetic in field, so obviously it experienced some kind of force. Due to that external force, the coil is trying to move, and when this coil is trying to move, the attached mirror is also moving with the same amount. Now, depending on this movement, I can measure the amount of current flowing through circuit, or sometime I can use this whole thing for measurement of a ballistic galvanometer. Now this is basically the cross-sectional part. This is the rectangular uh, area of the core on which the wire is wound up. This length is A, this length is B, and this is the axis of rotation. So from this point the phosphor bronze wire is connected, and the second last terminal, the opposite terminal, is also connected to another point. And if you saw this length, and these are the direction of force. Okay, so this cross-sectional area experience a kind of rotatory motion, rotatory force along this direction. So this whole thing experience a kind of torque. Now F is basically N I, A is the length, into B. So I is the amount of current flowing through this A, so N I B. And as this thing is rotating, F is along this direction, F is along this direction. This is the direction of magnetic field. So from the point of rotation from this force is basically F cross B by 2. Now there exists two force, F1, F2. So 2 into F cross B by 2 is the total amount of torque. So amount of torque is basically NIA B into cross B, as B is perpendicular to F. So this is NIA into B, so NIAB. AB is the area of the coil. Now if the equilibrium is established by this rotation, what happens to this phosphor bronze wire? When the coil is rotating through an angle theta, the phosphor bronze coil is trying to move the whole thing along opposite direction. So some kind of restoring force is present here, and the amount of restoring force is basically C into theta. So from this point I can get that NIAB equal to C into theta. So amount of current is basically C by NAB into theta. I know number of turn, total number of turn. I can calculate the area of cross section. I can calculate the external magnetic field, or the amount of magnetic field present for a horseshoe magnet at that particular point where this cross-sectional thing is situated, and theta is the angle of rotation. From the lamp and scale arrangement I can easily measure this. So from this point I can measure the current. Now this is the construction which I am talking a very little bit in the earlier, but in detail this is the constructional part or the basic part of the ballistic galvanometer. C, here you can see this is C, that is basically a metal frame, and on this metal frame some wire is winding up, and this metal frame is connected through F, a phosphor bronze wire, on which this mirror M is connected, and The C is another part of this coil is connected to a spring of made of phosphor bronze also. This is P, and the cylindrical iron core I is kept at the center of this suspended coil or rectangular coil. This is rectangular coil. Now, why the soft iron core is placed within the coil? First হচ্ছে to increase the magnetic field, magnetic flux in the gap, and second to provide uniform radial magnetic field in which the coil is rotating. So due to these two reasons, this iron core is absolutely necessary, and the mirror is also attached for the measurement. Okay, now this is a general theory of galvanometer. Now if you see here, consider a galvanometer that is in a closed circuit. Now the closed circuit means it is connected to a external circuit by which I can measure some amount of current, some amount of charge or something. Now as the ballistic galvanometer is made up of so many electrical things, that means where exists some spring, phosphor bronze, wire, and rectangular cross-sectional area, non-conducting obviously. So for this purpose, ballistic galvanometer itself has got some kind of resistance, so which is known as Rg, and it is connected to a circuit, so that circuit must have some external resistance. So Re is the external resistance of that circuit. Now the total resistance is basically R equal to Rg plus Re. That means resistance of this galvanometer and resistance which is present externally, or which is given to the circuit externally. Now E is the total amount of EMF applied to the circuit. Okay. Then the amount of current I is basically E minus G into d theta by dt divided by R. Now I can say how this G into d theta by dt term comes. This G into d theta by dt, this term basically represent the back EMF caused by electromagnetic damping force. Okay. Now how this d theta term comes, I can say you, as a coil is moving or with a velocity v at the right angle to the uniform magnetic field B, then obviously the induced EMF is basically B into V into A. Okay, so this is amount of induced EMF in the circuit B V into A. Now if this is the induced EMF, and due to this induced EMF or due to presence of this external force for this magnetic field, the coil is rotating, the angular velocity of the coil must be d theta by dt omega, and the radius of the rotatory circle on which this couple is trying to rotate the rectangular coil is basically b by 2. So the velocity is b by 2 into angular velocity, so b by 2 into omega. So velocity is basically b by 2 into d theta by dt. Now as a coil is two-sided coil, that means it has got two sides. The total amount of induced EMF is basically twice B into A into B by 2 into d theta by dt. Now this is B. A into B means area of cross section A into d theta by dt. Now as the galvanometer has got n number of turns on that particular rectangular coil, then total net induced EMF over a single coil is this. Now over n number of turn, the EMF becomes n times single coil EMF. So Na into B d theta by dt. Now NAB is basically equal to G, which is known as galvanometer constant. As NAB equal to G, then the torque is equal to NAB into E minus G d theta by dt. So this is basically amount of back EMF produced by the coil when it is moving. So total amount of EMF become E minus this back EMF. So torque is basically NAB E minus G d theta by dt divided by R. So G by R E minus G into d theta by dt. So this is the amount of torque for the circuit. Now, part of mechanics I must have to discuss for discussion of this characteristic galvanometer or any kind of galvanometer, I can say. Let us assume that Im is the moment of inertia of the coil about its own axis of rotation. The rectangular coil has moment of inertia Im. So the torque experienced by that particular rectangular cross-sectional area of the rectangular coil is Im d square theta by dt square. This is the torque. Now at the same time there exists a restoring torque C into theta, and there exists air damping because the galvanometer is moving within the rectangular coil is moving within the two horseshoe magnet of uniform magnetic field. So the amount of damping must be air damping, and in this case the damping force is obviously viscous damping, and the viscous damping is proportional to velocity. So damping force A1 to d theta by dt. Now total force is, here exists a torque, here exists a restoring torque, here exists a damping force. Okay, and obviously this is angular force, I can say, a dimension of torque. Now the equation of this coil become Im d square theta by dt square plus A1 d theta by dt plus C into theta equal to obviously the total amount of torque. So this equal to G E minus G d theta by dt divided by R. Now this equation becomes, I can move this G square by R d theta by dt in the left hand side and add this term with A1. So this becomes G B1. So Im d square theta by dt square plus B1 d theta by dt plus C theta equal to gamma, that is equal to G into E by R. Now this is the particular equation of motion of the coil under my investigation. Okay, or I have to solve this differential equation to calculate the motion of that particular galvanometer. Okay, now if I calculate or if I solve this differential equation, I can get the proper treatment of that galvanometer, and I can say when this galvanometer act as ballistic and when this galvanometer act as a moving coil. Now as this is the differential equation, I have to make this equation more simpler. To make this differential equation simpler, I have to assume something, that is P is equal to B1 by 2y, Q is equal to root over C by Im, and obviously F equal to G by Rim, and the equation becomes d square theta by dt square plus twice P d theta by dt plus Q square theta equal to F. So this is basically the differential equation of that particular galvanometer. Now as this is differential equation of a galvanometer, this equation must have two type of solution, but the two part of solution I can say. One is complementary function, another is particular integral. So in the first year session, or I can give a YouTube video for measurement of this uh, particular integral or complementary function. Okay. Mm, from that you can see this, how can you calculate the complementary function, how can you calculate this particular integral for any kind of differential equation. Numerous methods have been discussed in that particular section. So without going into details, let us focus our point. How can you solve this differential equation? So for the first, I have to calculate this complementary function. So as you know, everybody, I think you were well very familiar with solution of the differential equation, second order differential equation, obviously linear and the homogeneous differential equation. So for derivation of this complementary function, I have to make this right hand side equal to 0. Now this is the complementary function, and this is linear homogeneous differential equation. You can choose a trial solution theta equal to e to the power alpha t, and put this e to the power alpha t, theta equal to e to the power alpha t, in this equation. So the equation becomes alpha square plus 2p alpha plus 2q plus q square into e to the power alpha t equal to 0. Now that is a quadratic equation of alpha, and you can solve that quadratic equation to get the root, and the root becomes theta equal to e to the power pt c into e to the power root over p square minus q square into t plus d into e to the power minus root over p square minus q square into t. Now this p square minus q square, this term must have a special feature, or depending on the value of this term p square minus q square, the total function of the galvanometer is dependent. Okay, so if p square is greater than q square, then the galvanometer used in some way, and when the p square is less than q square, then the galvanometer can be used in some different way. I came in the section or the later part. And the second part is obviously particular integral. I am trying to solve this particular integral. You have already learned how to solve this particular integral. So yet for the recapitulation of this derivation, this is the particular integral. So f divided by d square plus 2pd plus q square, d is basically d by dt square, d by dt, and d square is basically d by dt square. Okay, so this equation becomes d square plus 2p into capital D plus q square to the power minus 1 into f, and if you, as f is constant, okay, so differentiating f with this two term become 0, and this minus 1, I bring this over here, okay, keeping 1 by q square common, and this differential equation I have to use the binomial theorem to expand this, and the equation becomes q square to the power minus 1 into f. So f divided by q square is basically the particular integral. Okay, now the total solution becomes this complementary function plus particular integral. Now as this oscillation, this term gives me, as t tends to 0, the oscillation becomes much higher. So this is not the acceptable solution. Now if t tends to infinity, the oscillation must dies out, the oscillation becomes 0, and as t tends to infinity, the oscillation becomes 0, then this particular integral at that time provide a special feature. Okay, and this part never becomes 0. So this particular portion gives me the steady deflection at t tends to infinity. And as this is steady deflection, theta steady is basically f by q square. So GE divided by R into C, E by R is equal to current, so GI by C. So this is basically the steady state solution of this differential equation. And as this is steady, from this point I can measure the current. So I have to set the galvanometer in such a way that it gives me a steady deflection, okay, for measurement of this current. Now how can you calculate the coefficient of, that is C and D? Now if you use the boundary condition at t tends to 0, theta equal to 0, and at t equal to 0, d theta by dt equal to 0. Now putting the first boundary condition in this solution, I can get that theta equal to 0 at t equal to 0. So this becomes C plus D plus this is theta S. So C plus D plus theta is equal to 0. And for the second part, or the second, applying the second condition, I have to differentiate the whole thing and put t equal to d theta by dt equal to 0 at t equal to 0. Now putting this second condition, I can get n into C minus D minus P into C plus D equal to C into N minus P minus D into N plus P, where this N is equal to root over P square minus Q square. So if you solve these two equations simultaneously, I can get C equal to N plus P by twice N into theta S and D equal to minus N minus P divided by 2 N into theta S. So this is the coefficient of these two. Now I have to put these two coefficient to get the complete solution. So putting these two coefficient, I can get theta is equal to theta S 1 minus e to the power minus pt divided by twice n plus p e to the power nt plus n minus p to the power minus nt. N is basically root over p square minus q square. Now in this case, as this is the solution, okay, now for measurement of a steady deflection requires a deflection attains at this steady point without any kind of oscillation. So I have to make the instrumental arrangement in such a way that the deflection becomes steady, or deflection kept at the final point at momentarily. Okay, so there will be no oscillation at all, and this happens when this theta becomes non-oscillatory. You can remember the forced vibration in your first semester syllabus, and you see there for forced vibration there must be a part of damping, that depending on the damping force the oscillation becomes critically oscillated or over damped motion. In those cases the oscillation becomes non-oscillatory and it attains theta s at some point. Now this happens when theta is non-oscillatory, and if theta is non-oscillatory then n becomes real. There will be no imaginary part or sinusoidal damping sinusoidal part present in this equation. So if n is real, then this equation becomes this equation gets a steady deflection. For non-oscillatory equation, p square must be greater than q square. So this is oscillatory, aperiodic, or overdamped behavior. Okay. Now as p square is greater than q square, p square is basically b1 square by 4i square. This should be greater than c by im. So this part must becomes greater than 4im by c. So these are the condition of a steady oscillation of this galvanometer. Okay. And for oscillatory nature, when this becomes oscillatory, then p square is less than q square, or the equation satisfies this relation. That means a1 plus g square by r whole square less than 4im by c. Now that n becomes negative, or n equal to, as this is root over p square minus q square, so this n equal to root over minus 1 into q square minus p square to the power half. So j into omega, where omega is this. Now the equation becomes theta equal to theta s 1 minus e to the power minus pt by 2j omega p plus j omega e to the power j omega t plus j omega minus p e to the power minus j omega t. If you put this part in this equation, you can get the thing easily. Okay, so this equals to basically e to the power minus pt, theta is into 1 minus e to the power minus pt, p by omega into sin omega t plus cos omega t, right? So this is, as sin omega t and cos omega t are present here, so the motion becomes oscillatory, and obviously this oscillatory nature becomes diminishing as minus sign is here. So from this theta s, or the steady point, it becomes less oscillatory. Okay, the oscillation is dies out. Okay, as the time progresses. Now this is the term. I have to arrange this whole part, and theta equal to theta s 1 plus am e to the power minus pt sin omega t plus alpha. You can solve this part, or I have already solved this in different classes. How can you arrange these two coefficients in such a way that this equation reduced to this particular way? Now am is basically amplitude of oscillation, and this amplitude becomes root over p square by omega square plus 1, and this phase part alpha becomes tan alpha equal to omega by p. And this, in this case, I can see here it is a sinusoidal type damping present in the circuit. Okay, so we get damped sinusoidal oscillation of the both side of mean theta s. Now as t tends to infinity, t becomes infinity, so this term dies out as minus p into t. This becomes 0, and the oscillation gets to a steady part, theta s, and the time period is basically twice pi by omega. So twice pi root over q square minus p square, so twice pi root over c by I into this. So as r increases, a time period will decrease. Okay. Now the rate of decay is determined by e to the power minus pt. So e to the power minus pt is a factor which determines how these things are decaying. Okay. So the term e to the power minus pt plays a crucial role here, because this e to the power pt determines that how this oscillation dies out. From the previous equation you can see here that e to the power minus pt is a term which makes this oscillation gradually in decaying, or makes the oscillation under damping. Now the rate at which the amplitude is decaying is determined by e to the power minus pt, and the rate at which the amplitude is decaying is basically exponential e to the power exponential minus pt. So exponential minus a1 plus g square by r into t divided by twice m. Now this is a curve of time versus oscillation of the galvanometer. This black straight line, this represent the steady portion of the ballistic galvanometer, and this theta s is basically a steady solution, right? Now as I mentioned here, in this solution you can see that theta is constant. Now around this theta end, sometimes amplitude becomes maxima, sometimes amplitude becomes minima. So in the both side of this theta s, the oscillation is running. This is maximum, this is minimum, this is maximum, this is minimum, in this way, right? And at the same time the amplitude becomes gradually decrease by a factor e to the power minus pt. Okay, so this black line represent the underdamped motion, or in that case damping is not so high, or I can say the damping force must be less than the natural magnetic force exists in the circuit, or the damping frequency, the force frequency is less than the existing force here. On the other hand, if p square is greater than q square, the oscillation starts from here, and the indicator is rising with the rise of the current, and it is rising in such a way that after some time, momentarily it is not getting to a steady point theta s. At an instant of time it does not show deflection of theta s, but as the time goes, as the time is moving, the amplitude of this curve shows the asymptotic nature, with respect to this theta steady point. So after some time it reaches to a theta point or the steady point. And I have discussed in my previous part for this overdamped motion. So this is overdamped motion. But this red line, this is a special feature of a galvanometer. And obviously this red line indicate how can you use a galvanometer. Means how much amount of resistance you should have to put to make this galvanometer oscillatory in nature for measurement of charges. And from this curve you can estimate the value of critical damping resistance of the galvanometer. Right? Now come to the theoretical part. As you see here, remember the forced oscillation. In that case, when the damping force becomes in such a way that the oscillation attains a steady point, okay, or from this equation n equal to 0. So the equation becomes 1 minus e to the power minus pt by twice n. So this is undefined, okay. Now come to this equation. This is steady and this omega is critical. This omega becomes root over q square minus p square all equal to 0. So am e to the power minus pt into sine alpha, right? So it shows the exponential rising of theta s. At t tends to infinity or t tends becomes larger, the equation starts from this point and moving to a steady part, this, okay. So this is basically critical damping. Now the oscillation becomes non-oscillatory, or it does not swing around the steady point, and for this case n becomes equal to 0. As n equals to 0, p square equal to q square, or a1 plus g square by r total whole square equal to 4im by c. Now normally we are constructing the instrument in which the rectangular coil is kept within the horseshoe magnet, so there exists no other damping than air, and for air damping we can neglect the term a1. So the equation becomes g square by r its whole square equal to 4im by c, or g to the power 4 equal to 4im c into r square. So r is equal to g square divided by 2 root over im into c, where g is the galvanometer constant, im is the moment of inertia, c is the coefficient of restoring couple, and this resistance is an estimation of the external critical resistance applied to the circuit to make the circuit under damped or oscillatory in nature. Now as I mentioned here, this red curve shows the critical damping. Now what is this CDR? The CDR, I can say here, for a ballistic galvanometer will oscillate if it has not been properly damped, okay. Now galvanometers are damped by adding an external shunt resistance of just the right amount of resistance in parallel with them. Now this proper amount of resistance at which the motion is just cease to be oscillatory, or the motion becomes oscillatory in nature, for adding that particular shunt is known as critical external damping resistance or critical damping resistance. So I have to use the resistance greater than this critical damping one to make the circuit oscillatory in nature. So thank you once again for listening.